Good morning from here in London. Thank you for joining us for today's webinar with a look at chemical processing. Today's topic will be looking at multi-physics problems in mixing applications, a path via simulation. The corporate bio, if you will, over with. We're delighted to have two speakers for you today. We have a first off guest speaker, Alex Smith, who is an experienced CFD engineer and chartered chemical engineer, currently leading the process engineering group in CPI's industrial biotechnology platform. After graduating from Leeds in 2007, university, Alex joined the graduate development program at Siemens Metals Technologies, working the design and commissioning of blast furnaces. Over a 7-year period with Siemens, Alex contributed to the successful startup of a new rebuilt blast furnaces all over the world, including periods working in India, Brazil, and across Europe. He then joined CPI in 2014 and his current role, and has used his experience in engineering and CFD modeling to provide valuable support to companies. We also have, after Alex's portion, we have Thomas Eppinger, who is an application specialist for the chemical and process industries here at Siemens for the STS, that's the Software and Test Solutions subsegment. Within his role, he's responsible for expanding the use of CFD into new application areas, along with bridging the gap between software development and Star CCM Plus users. He graduated from the Technical University in Berlin and joined what was CityAdapco in 2006 as a support engineer in Nuremberg. And since 2013, Thomas is working in his current position. Okay, now that we have the bios over with, I'd like to hand over to our guest speaker today, Mr. Alex Smith.
Thanks for the introduction there. So yeah, I'm Alex Smith from the Center for Process Innovation. And I'm going to just give you a quick rundown today of essentially how we use CFD to support process development and scale up. So just a bit of a quick agenda. So I'll start off with a quick introduction to CPI, kind of who we are, what we do, just to give a bit of context to the examples that I'll follow up with, and then yeah, there will be 2 examples. So who are CPI? So we are an independent open access technology innovation centre. We were set up by the UK government around about 14 years ago now, to help companies to scale up and develop their sort of new and novel processes, basically. So we sit in this space in between invention and industry. And we basically exist to help people across that gap. So we have so how we do that. So we have a variety of experienced scientists and engineers who've spent years and years scaling up processes. We also have a whole load of pilot and demonstration scale assets as well. What a lot of companies find is some outrageously large percentage of good ideas tend to die in the scale up phase, purely through financial reasons, for lack of the ability to get hold of this kind of scale of assets that you need to prove a process. So that's where we come in, basically. We have 4 centres, 4 national centres. So the Printable Electronics Centre, the Industrial Biotechnology Centre, which is where I work, Biologics Manufacturing, and the National Formulation Centre. And these were each set up to assist assist the development of a particular industry within the UK. Okay, so in terms of specifically CFD at CPI, how do we use it? What do we do with it? So mostly for us, it's about generally getting a better understanding of what's going on inside our vessels. That can be in the form of troubleshooting. So something isn't behaving quite as it should be. You can't necessarily figure out why just through looking at single point instruments alone and looking through sight glasses and things like that. What the CFD helps us with there is it helps us to see in much greater detail what's going on inside of our vessels, to kind of help us to narrow down what the issue might be. Process characterization and optimization as well. So basically for an existing process, how can we make it better within the limitations of an existing piece of kit? Process scaling. This is one of the examples I'll give a little later on. That's one of the main things we do is essentially trying to move people's processes from laboratory scale, kind of in a flask of 1 litre or less scale up through to an industrially relevant scale. So how do we can use CFD to support that process by better understanding the performance limitations that come with scale, and then design and operational guidance as well, and virtual prototyping. So given completely blank sheet of paper, what would our process look like? Okay, so the first example I'll go into here is about using CFD to support scale up and also scale down. And I'll just introduce that concept of scale down, because it's a big part of how we operate here. In that we have a variety of assets, as I mentioned earlier on, from kind of milliliter scale fermenters right through up to 10,000 litre scale. And what we need to do is to help our customers understand the limitations of the larger scale operation, without actually having the cost of running at large scale. So what we try and do there is to find ways to operate small scale vessels in a way which mimics the performance of large scale vessels and the limitations of large scale vessels. So we can kind of help companies to do all of their kind of risky experimentation at small scale cheaply, but in a way which is relevant to large scale. One of the main issues we come across time and again is people bringing in processes which have been developed in the lab using lab scale fermenters which are running flat out, which is just unfortunately not relevant when you get to, or not representative of larger scale operation. Okay, so I'll give just to kind of introduce the concept of using CFD to assist with process scaling. I'll just use a very simple generic example to start with. So if you're designing a stirred tank reactor on paper, there are a variety of traditional sort of rules which you would use here when it comes to either the physical design of your vessel, or also the operation as well. So, for example, with your physical design, you'll have things like your impeller should be 1/3 of your tank diameter. You should have 4 baffles, and they should all be 10% of your tank diameter. Things like this, and the same comes to your operation as well. So, I've just listed a few here. So, to match mixing performance, you should match the impeller tip speed. To match solids distribution performance, you match energy input, and so on. These are well-established rules which have been used for years and years, and people tend to trust them. But what we'll do here is essentially just a little exercise in using CFD to kind of check these rules, but also to see how much further we can go just by exploring around the edges. So what I'll pick on here is one particular example, which is this: to match mixing performance, you should match the impeller tip speed. So I've got a very simple example here where I have two vessels which have been perfectly geometrically scaled. Essentially, I've just taken one vessel, a 500 ml vessel, and just stretched it in all dimensions equally to make it 5 litres. At the start of the video here, both vessels are stirring at 500 RPM. And what I'll do is, you can see we've got here the turbulence profile shown on both of them. What I'll do here is I'll gradually increase the speed on the right-hand side until the turbulence profiles are the same. That, in theory, according to those rules, should be at the same tip speed. And what we'll find here is, when we get up to speed, basically we are around about the same tip speed, but not exactly the same. So what this shows is that the model is generally in agreement with these traditional rules which everyone's trusted forever. However, what it is showing is that we can we can go in the smaller vessel. We need to go slightly beyond the same tip speed in order to get exactly the same turbulence profile. So that's all well and good, but actually, how often do you have places which have perfectly geometrically scaled vessels? We find that's quite rare. Actually, what we end up with normally is people who have a research lab with a variety of different vessels in there. So what I've got here is a same example again, except on the right hand side we've got a disproportionately small impeller in there. So if we do the same exercise again, so essentially speed up the agitation speed on the right hand side until we have the same or as close to as possible the same turbulence profile. What you see in this case is, because they are not perfectly geometrically scaled, these rules just go out the window, and actually we need to go way beyond the same tip speed in order to get the same value of turbulence and the same kind of mixing performance there. And this is, for us, this is where CFD comes really in handy, particularly when it comes to things like comparing our small-scale vessels against a customer's small-scale vessels to try and mimic the performance that they were getting in their labs, in our labs, as we transfer the process in, things like that. So how does this apply to, how have we applied this kind of approach to generally how we do things here at CPI? So what we've done is, over the last kind of 6-12 months or so, we've developed a suite of CFD models looking at the performance of all of the different scales of fermenters that we have here, from a point of view of various kind of key performance criteria that come with fermentation processes, so liquid mixing, KLA and mass transfer, gas hold, bubble size, and so on. And we've one of the advantages we have with actually having the assets as well is we can validate our models on our own assets. So what we have here is just two plots of mixing performance or mixing time, one for our 10,000 litre fermenter and one for our 150 litre fermenter, just showing the mixing profile predicted by the CFD model against the mixing profile actually measured in an experiment, and you can see they draw pretty much the same lines. So what we actually get from this is a plot like this, and this is where, when I was mentioning before about scale down modeling, this is where it becomes really useful. So we can see here, this is mixing time, so this is the minimum and maximum reasonably achievable mixing time for each of the vessels we're showing here. And what we can see is we can achieve the same mixing time as the 10,000 litre vessel in as small a scale as 10 litres. So now we know essentially how to operate the 10 litre fermenter in a way which has the same mixing performance as a 10,000 litre fermenter. So we can do all of our experiments at 10 litre scale, where it's relatively cheap on materials and labour and things like this, get a really good understanding of how the process is going to work, optimise the process at that scale, and then in theory just chuck it straight up to 10,000 litre scale and it'll just work. Same applies to KLA and mass transfer rates, same kind of exercise. So that was just a brief introduction to scaling processes and how we can use CFD to support that. What we've got here as well is an example around getting the best out of a single piece of equipment. So this is about how to wrap our heads around the limitations of operating a very large scale. So this slide just shows some of the issues you get with a fermentation when you get to very large scale. When you're operating in a lab scale, you have mixing times in the order of single-digit seconds. When you get to kind of 10,000 litre scale and above, your mixing times can be in minutes. And what this means is when you make an addition at the top, if you're adding your sugar, for example, at the top, it can take minutes to get down to the bottom of the vessel. What you find is actually you end up with the concentration profile that looks a little like this, where you're quite heavy at the top, and by the time you get to the bottom, it's all been consumed. Same with the oxygen, the air's coming at the bottom. by the time you get to the top, it's all been consumed. So what we wanted to know is we wanted to have a look at our larger scale vessel and really kind of understand what is the best way we can operate this to get the most possible mixing performance out of it. So what I've done here is we did a series of mixing time models, just with a tracer added in at the liquid surface at different levels, and we monitored the concentration profile of that and the uniformity of that over time in various different mixing zones. We saw some quite interesting results from this. So this is a similar plot to what I'd shown before, which is the mixing uniformity, or the volume uniformity of the concentration of the tracer over time in various different mixing zones. So between the first and second impellers, between the second and third impellers, above the third impeller, and then overall throughout the full vessel. We see some quite interesting things here. So this is a liquid level kind of just roughly in the middle of the first and second impellers. If we fill the level a little higher, what you'd expect is there's more fluid, it will take longer to mix, but what we actually see is it takes less time to mix. And this would be quite difficult to explain without the CFD model behind it. If we just look at these plots here, what you can see here is we have a nice sort of recirculation pattern generated here, but if we pull the level back down again, we actually don't get this recirculation pattern. So actually what happens here is in between the impellers, at a larger fill volume, we actually have a better mixing performance. If we fill up further and introduce the next mixing zone, you can see the time extends out, as you would expect, as we brought another zone into play. But then again, the same applies if we increase the level within that zone. It actually pulls the mixing performance back again, because again we have an opportunity to create a nice recirculation pattern there. And then again, as you'd expect, as we go up to the top, we see all of everything go out again because we're introducing another mixing zone. What we see here though is actually the mixing performance within each of the three zones, which would be very difficult to measure without the use of CFD. We see here that the top zone mixes quite quickly, and the sort of second and third zones mix at essentially the same rate, just offset by a period of time, which would be the period of time it takes for the fluid to actually make its way down there. Okay, I think there we go. We got there in the end. Okay, so basically that was it. Just a couple of introductions, a couple of examples of how we use CFD to support what we do here at CPI, and that's me.
So yeah, also a warm welcome from my side, and I would like to start with a summary of some trends we see in the chemical and process industry based on our interaction with our clients. So first of all, there is a need to improve the performance, mainly with a goal to increase the throughput. Secondly, we see a trend to more flexibility. And this can be either with respect to the feedstock for a certain process. So if you think, for example, we see a certain transition from carbon-based chemistry to green chemistry. But it can also be with respect to material variability. So it means that smaller batches are needed to produce more customized products. And this often takes place in the same reactor. And finally, and this is probably always true, we want to reduce costs by, for example, reducing the power consumption for a certain process, or by doing fewer expensive tests, or indirectly by reducing the time to market. And for all these trends, we believe that CFD simulation may help to achieve the goals by either helping to predict and understand the reactor behavior, and or by finding better designs or operating conditions for a certain process, and therefore creating engineering innovations and business value. But obviously, to use CFD successfully and efficient, some key requirements must be fulfilled. And first of all, we need obviously the ability to import CAD models from external sources, or we should be able to create it within a tool. Secondly, also robust meshing is needed to capture complex geometry and also resolve areas where we expect large gradients, like for example here around the impellers, and also special areas of interest needs to be resolved appropriately. And this means that we need an easy control of local mesh refinement. Then obviously for the simulation, suitable and validated models for all relevant physics should be available. And this is even more important, I believe, if you think about the time it typically takes to implement and test a new model into an existing code. This can often not be done within 1 or 2 days, so and it typically consumes really a lot of time. And then we need also a powerful data analysis, not only for visualizing the simulation results, but also for quantifying parameters and understand the complex independencies. And I will show you in a few slides some examples on that. And finally, especially if you think about repeating work, a certain degree of workflow automation is extremely helpful for efficient simulations. And StarCSim Plus offers this already with its pipelined and adaptable workflow. But we are also offering Admixtus, and Admixtus is an add-on to StarCSim Plus. And Admixtus is designed to guide the user in a step-by-step way through the complete setup of mixing vessel simulation. And this includes the CAD creation, where the user can select and customize different vessel types, impellers, baffles, and internals from an internal library. It helps for the mesh and physics setup based on best practices. So means the meshing process automatically includes certain refinement levels around the impeller, around the baffles, at the cooling or heating walls or internals. And finally, Admixtus also offers a broad variety of typically used parameters, reports, and scenes, so they can easily be just selected, and then everything else is done in the background. And with that tool, with Admixtus, you're really enabled to set up a mixing vessel simulation within minutes. And since it is fully parameterized, it can also serve as a starting point for a design space or operating condition exploration with the built-in design manager in StarCSim Plus. So that I can summarize that StarCSim Plus fulfills all these requirements to predict, understand, and improve design variants and operating conditions efficiently. Okay, so this was a pretty general introduction. So now I want to get a bit more specific, and I would like to start with a simulation of solid suspension cases. And here, the first example deals with impeller power input for different solid loadings in a mixing vessel with a pitch blade turbine. The case itself was simulated using the Eulerian multiphase model with a granular flow extension to take the particle-particle interaction into account. And the advantage here of the Eulerian multiphase simulation is that it solves only one full set of Navier-Stokes equation per phase, which is coupled via the volume fraction and the exchange source terms. And therefore it is well suited, especially for cases where we have a large amount of particles, of solid particles. And yeah, here on the right-hand side, you can see a snapshot, basically the solid distribution in a cross-section for different solid loadings. The simulation were always run with the same impeller speed. And now if we look And now if we look at the power consumption, then we see that we are predicting, or we see in the experiments that we have a nonlinear increase in the power consumption versus the solid loading, although the correlation typically predicts that the power consumption is a linear function of the solid loading. And with Star System Plus and with our simulation, we are also able to capture this nonlinear behavior. So, which means that the non-uniform distribution of the solid particles in the tank leads to this nonlinear behavior, and this can be predicted with the simulation. But obviously, it's hard to incorporate this into a correlation. Okay, but what if we are interested really in the individual particles? So Star System Plus offers the discrete element method, where we are really resolving all these particles, and we are also resolving the particle ball collision, as well as the friction and the effect on the background fluid. So with that, we have a very detailed model for the analysis of solid suspension. And in this case, we are looking at the amount of suspended particles for different impeller frequencies in a pretty high viscous liquid. So as you can see, the dynamic viscosity is around 1 Pascal second, and this means that it's a laminar flow. So, and here on this slide, you see for 3 different impeller speeds the suspension state. On the left, only a few particles are lifted, in the middle some more, and obviously on the right-hand side, you see that a lot of particles are suspended. And if we look at some quantitative results, so basically the amount of solid suspended versus the impeller frequency here on the right-hand side, then we see a reasonable good agreement between the experiments and the numerical simulation. Especially with respect to the frequency range, where we see the transition from the sessile to the suspended state. This is pretty well predicted. And this predictive capability is even more important since there's, at least not to my knowledge, no correlation in open literature available to predict the solid suspension states in the laminar flow regime. Okay, so the next topic I would like to talk about is heat transfer, and with that I would like to start with a kind of thought experiment. So assume we have to deal with a reactor where a chemical reaction occurs. So first of all, we have to mix 2 components, and due to the chemical reaction, there's also a heating or cooling required. And we did now some experiments in the lab, and we want to scale it up. And what does it mean? The heat of reaction basically scales with the volume, while the cooling or heating area only scales with the area. And this discrepancy could lead to some issues. So typically it means we need to add some more additional cooling capacities, which can, for example, like this, so that we have more windings of the cooling or heating coils, which on the other hand can affect the flow, and the flow can again affect the mixing and finally the mixing performance. So we have a strong dependency on several aspects, and with CFD we can easily investigate different design variants and how they affect the reactor performance. And together with the Hochschule Sachsen-Anhalt in Germany, we are looking at the moment into a heated mixing vessel with a cooling jacket. And what they found is basically that depending on the inlet and outlet position and the angle, they see completely different cooling and heating, or cooling in that case, behavior. And this is something they would like to understand better. And in addition, they are also thinking about investigating if really the impeller Reynolds number is the best choice for using into heat transfer correlations at the outer wall. But yeah, mainly we are looking at the cooling here. And a short comment on meshing. So typically, and this is shown here on the left-hand side, we need a certain cell resolution around the impeller, for example, to predict the power number or power consumption correctly. But for the heat transfer problems, the most critical part is here the meshing around the glass wall. And this means basically the resolution of the boundary layer as well as of the glass wall. And we need an accurate boundary layer, obviously, to calculate the heat transfer correctly. While for the thin glass wall, it's slightly different. So here we are dealing more with a number of cells which are generated. And if we apply such a polyhedron cell here, then typically we end up with a huge number of cells, which is not necessary. But Star Cesium Plus offers also the thin measure, which is able to generate in thin areas, so in small gaps, a suitable mesh with not too many cells. And this is really beneficial for this kind of application. So then some results, some preliminary results. So first of all, okay, and this mixing vessel, the heating elements are applied directly on the impeller blades. And what we are seeing is basically that in the vessel we have a extremely homogeneous distribution of the temperature. This can also be seen here in this histogram plot. So basically we have a very narrow distribution, some changes around the impeller, directly at the impeller and at the wall, but basically we can assume the assumption that it is an ideal mixing vessel holds for the temperature distribution. But what we also see is that the heat transfer coefficient, as shown here on the vessel wall, is very non-uniform. So we have pretty high values here in that area, basically here. And we have also areas where the heat transfer coefficient is pretty low. And this is basically affected or caused by the flow in the cooling jacket. And this is also the explanation why typically the inlet and outlet has a very strong effect on the heat transfer, and that the correlations typically cannot predict the behavior very well. Okay, sorry. Another class of problems is the interaction between the fluid flow and the structure itself. So structure in this case means the baffles, the impellers, all internals. And in most cases, in mixing vessels, the one-way coupled problems are sufficient. So basically, we have some fluid loads acting on the internals, on the impellers, and the structure itself affects the fluid flow not significantly. In most cases, it's negligible. And in this study, we were looking at the solid stress on the mixer shaft in a baffle tank. So we have 4 baffles and a Russian turbine with 6 blades. And the final outcome basically is a very regular periodic stress signal. And if we do a fast Fourier transformation, then we see that we have a perfectly match between the stress frequency and the blade to baffle passing frequency. So that the results itself are as expected. And also, especially for this case, for this specific case, the stress level is pretty low, so that we can assume that fatigue on the shaft is not be expected. But obviously, we can also, as shown here, use our built-in morpher to basically modify the impeller so that the stress the stress acting on the impeller leads to a certain displacement, and this can be considered. But even in that case where we have pretty strong forces acting on the impeller, we still need a deformation scale factor of 50 to make it visible that the blades are really deformed. So typically one can assume that incorporating the changes of the geometry is not necessary in mixing vessel simulation, also not in that case. Okay, and the final topic I would like to talk is operating condition exploration in a fermentation reactor. And as Alex said, fermentation reactors are pretty tricky and complicated equipment. So this is a schematic scene of an aerated mixing vessel. So we have here at the bottom a sparger where gas bubbles are injected into the vessel. And obviously, to be predictive, we have to capture the fluid dynamics, and fluid dynamics in this case means it's a multi-phase fluid dynamics. We need to capture the flow field correctly, the gas hold up. We often have to deal in fermentation reactor with non-Newtonian liquids. Then obviously there is a mass transfer from the gas bubbles to the liquid. This mass transfer has to be modeled, and the mass transfer is a function of the interfacial area, and especially in full scale tanks, size distribution has to be considered, which includes coalescence and breakup, so the change of the sizes. And in addition to that, we have some microorganisms in the tank, and this leads to, or the microorganisms are responsible for certain reaction. They have to be modeled, and here we are facing another challenge, and typically the timescales are vastly different. So if you think about the fluid flow, this maybe takes some seconds, or as Alex said before, maybe some minutes until you have distributed everything. But the reaction part typically takes days, sometimes weeks, or even months. So if you think about wastewater treatment plants, for example. So we have a broad variety of issues to handle with. I would quickly highlight one aspect, and this is the simulation of the size distribution. So in the optimization or in the operating condition exploration, I will show in a few slides. We were using the Eulerian multiphase model, and the Eulerian multiphase model. There are two models available to include population balances, so the S-gamma model and the adaptive music model. And the S-gamma model is basically a very efficient method to include size distribution, because we are only solving transport equation for two additional parameters, so the zeroth and the second moment. But obviously, since it's very efficient, it has also some drawbacks, and one of the drawbacks here is that it assumes that the size distribution has to be the size distribution shape has to follow a log normal distribution. In a lot of real world application, this assumption holds, but obviously not in all. But for these cases, we have implemented recently the adaptive music model. This is an extension of the classical music model, and the classical music model divides a certain size distribution in a certain number of groups, and for each of these groups, a set of transport equations is solved. And you can imagine that if you solve in each cell, each of these size groups, it's a large computational overhead, especially in areas, for example, where you have only large bubbles. Then you still have to solve for the small ones, and in areas where you have small bubbles, you still have to solve for the large bubbles, which is not very effective. And the adaptive music, basically, it adjusts the size distribution in each cell. So we see a dynamically shift of the size groups over the whole geometry, and with that we are able to capture the size distribution with fewer classes and significantly fewer classes, which makes the simulation much more effective. Okay, so now back to the operating condition exploration. So our goal is basically to minimize the power consumption. And since the variables we are varying is the volume flow, the Sparger volume flow, and the rotational speed, we are considering for the total power consumption the compressor power as well as the impeller power. And our goal is to maximize the volume averaged dissolved oxygen. And in addition, because most of the microorganisms are stress sensitive, we want to keep the local stress below a certain value so that the microorganisms are not getting damaged. And with that, we run this operating condition exploration at Star System Plus with a design manager. And we run in total 164 different simulation, and each simulation took between 10 and 30 minutes, depending on the boundary condition, so that this study can be done over the weekend, for example, depending on the cluster sizes. And now on this plot, basically each of these circles represents one design. And the larger the circle, the higher the impeller rotation rate, and the color indicates the Sparger volume flow. So based on this map, we can now remove all designs where the strain rate is too high. So basically, at least locally. So where we can assume that the microorganisms get destroyed. Then we can also remove some designs on the left-hand side, where the mass transfer of oxygen from the gas bubbles to the liquid is too low, because we were assuming that microorganisms are consuming a constant amount of oxygen. But all designs in the white area, they are valid designs, and we can now pick the design which best fits our requirements. And I just want to quickly discuss these two cases. So basically, we have more or less the same power consumption, but we see a significant difference in the amount of dissolved oxygen in the tank. And this can be attributed to the fact that we have a higher gas aeration rate in case 1, which leads to a higher volume fraction compared here to the case 2, where the volume fraction is lower. But also with the higher volume fraction, the coalescence probability is higher, means our mean outer diameter is slightly higher compared to case 2. But overall, we see that the amount of dissolved oxygen in the tank is about 20% higher than in the other case. So, and this means basically with the same power consumption, we can achieve a better reactor performance, or if, for example, we would assume that the amount of dissolved oxygen of 4.5 is sufficient, we could maybe just pick a design which is more based here, and with that we can reduce the power consumption, so that we have different strategies to optimize our reactor. And with that, I'm done, and I'm looking forward to answering your questions if you have any.
So it just remains me to say thank you to Alex Smith from CPI, and of course thank you to Thomas Eppinger. With that, the session is closed. Thank you to you all. Goodbye.